This is the video on counting and probability. So in this video we're putting together what we know about counting and what we know about calculating probabilities. Actually our goal in doing all the counting that we did, the fundamental counting principle, permutations and combinations, was all aimed at being able to calculate more complicated probabilities. So just a reminder that if you're calculating the probability of an event, it will be a fraction. The number of outcomes where the event occurs over the total number of outcomes. This is, in a nutshell, what we know about calculating probabilities. You can also express this as a decimal or in percent form. And now we're going to just look at a lot of examples for the remainder of this video. So here we have a small lunch counter that has a menu consisting of 5 sandwiches, 4 drinks, and 3 desserts. We're assuming that one of the sandwiches is a grilled cheese, one of the drinks is iced tea, and one of the desserts is vanilla ice cream. And we want to know the probability that you order these 3 items if you make a random order. The word "your" that was there should be a "you," and I've made the correction. So what is the probability that you order exactly these 3 items: grilled cheese, iced tea, and vanilla ice cream? So we're first going to count the total number of possible orders. This is something we've done before. So in this situation, to place an order, we're making 3 choices. We are first choosing a sandwich, and then a drink, and then a dessert. So this is the kind of situation where the fundamental counting principle is used. We're making 3 choices. The choice of sandwich can be done in 5 ways. The drink can be chosen in 4 ways, and the dessert in 3 ways. So the number of ways of placing an order is 5 times 4 times 3, which is 60 possible orders. The order that we're talking about here, grilled cheese, iced tea, and vanilla ice cream, is just one of these 60 orders. So the probability of placing this order, if you order randomly, is 1 over 60, or in decimal form 0.01677. I've rounded off that last digit. Okay, a second example. You roll 2 fair dice. One is red and one is green. So first of all, how many possible outcomes are there if you roll a red die and a green die? So 6 possible outcomes for the red die and 6 possible outcomes for the green die. So for the 2 dice together, there are 6 times 6, or 36 possible outcomes. And now here's a probability question. What is the probability that you roll an 8? In other words, what's the probability that the 2 numbers that are face up on the 2 dice add to 8? Well, we need to know in how many of the 36 possible outcomes the 2 numbers add up to 8. And here they are. If you roll a 2 on the red or a 6 on the green, you get an 8. 3 on the red and 5 on the green. Those numbers add up to 8. 4 on the red and 4 on the green. 5 on the red and 3 on the green. And finally 6 on the red and 2 on the green. It looks like there are 5 possibilities for rolling an 8. So the probability of rolling an 8 is 5 over 36. the number of outcomes where you roll an 8 divided by the total number of possible outcomes. 0.13889. Another example, you pick 4 of the 10 digits 0 through 9. No repeats. You're picking 4 different digits at random, and then we are writing them in some random order. The question here is, what is the probability that you have chosen the digits 1 through 4 and that you wrote them in their numerical order, 1, 2, 3, and 4? Well, if you choose 4 of 10 digits and put them in order, that's a permutation of 10 things taken 4 at a time. And we know how to count the total number of ways of doing this. Actually, we have 2 ways, really. You can use the fundamental counting principle. You're making 3 choices: the first digit, the second digit, the third digit, and the fourth digit. The first can be done in 10 ways. The second you choose from the remaining 9 digits can be done in 9 ways. The third in 8 ways, and the fourth in 7 ways. Or you can use permutations. Taking 4 things out of 10 and putting in order is the number of permutations of 10 things taken 4 at a time, 10 NPR4, which can be done on a graphing calculator or on Desmos. 5,040 possibilities for choosing 4 digits out of the 10 possible digits and putting them in order. Choosing 1, 2, 3, and 4 and writing them in numerical order is just one of these possibilities. So the probability of doing this, of choosing 1, 2, 3, and 4 and writing them in numerical order, is 1 over 5,040, 0.000198. Moving on to the next example, choosing a slate of officers. So we have a club in this example consisting of 12 female and 10 male members. A slate of 3 officers, president, vice president, and secretary, is to be chosen randomly. And we want to know what is the probability that all 3 officers are female. So as we know, choosing a slate of 3 officers from the 22 club members is choosing 3 of 22 things and putting them in order. This is a permutation. So the 3 officers can be chosen in 22 NPR3 ways, the number of permutations of 22 things taken 3 at a time. Which is 22 times 21 times 20. If you use the fundamental counting principle, either way, 9,240 possible slates of officers. Now we need to count the total number of slates in which all the officers are females. So to do that, we're choosing 3 of the 12 female members and putting them in order. This is also a permutations problem. Taking 3 of 12 objects and putting them in order is the number of permutations of 12 things taken 3 at a time. Not too hard to calculate it by hand. 12 times 11 times 10. 1,320 ways of getting a slate consisting of all female officers. So the probability of a slate like that is 1,320 divided by 9,240, or 0.14286. Another example, from a group of 8 adults and 13 children, we're selecting 6 people randomly We're not putting them in order. No order is involved here. So what is the probability that all of the people selected are children? Well, if you are selecting 6 people from a group of 21 people and not putting in order, that's a combination. The number of ways of selecting 6 people from the 21 people in this group is 21 NCR6. It's the number of combinations of 21 things taken 6 at a time. 54,262 possible ways of selecting 6 people from 21. And now we need to know the number of ways of selecting 6 of the 13 children. So if you are selecting 6 of 13 children and not putting them in order, this is a combination of 13 things taken 6 at a time. So it's 13 NCR6, which is 1,716. Therefore, the probability of selecting 6 children is the number of groups of 6 which have 6 children divided by the total number of groups of 6. That would be 13 NCR6 divided by 21 NCR6. We have calculated both of those numbers. If you write the fraction in reduced form, you get 66 over 2,087. It's not really necessary to do this. And if you write this as a decimal, 0.031624. And now let's look at a few probability problems involving hands of cards. So here once again is the composition of an ordinary 52 card deck. So this will be important in these probability problems we're about to do here. This is a picture we've seen a couple of times before. The 52 cards are arranged into 4 suits: clubs, diamonds, hearts, and spades, each suit with 13 cards: ace, 2 through 10, jack, queen, and king. Ignore the bottom 3 cards in this diagram as usual. And just a reminder, when we're counting card hands, we have decided to use combinations. So try a few sample problems. 5 card hand is chosen from an ordinary 52 card deck. How many hands are possible? This is a combinations problem. Combinations of 52 things taken 5 at a time. 52 NCR5, 2,598,960 possible 5 card hands. I think we've seen this number before. So now suppose a single card is drawn from an ordinary 52 card deck. And we want to know what's the probability that this card is the 9 of hearts. Well, the 9 of hearts is only one of the 2.5 million or so possibilities. Whoops. Sorry. The 9 of hearts is only one of the 52 possibilities if you're drawing a single card. Sorry about that. So the probability is 1 over 52, in decimal form 0.01923,077. Now let's suppose we take a 5 card hand from an ordinary 52 card deck. We saw on the previous slide that there are more than 2.5 million possibilities for a 5 card hand. And we want to know here the probability that all 5 cards in the hand are clubs. So to get a hand consisting of all clubs, we are choosing 5 of the 13 clubs and not putting in order. Remember, we use combinations when dealing with hands of cards. So the number of ways of doing this is the number of combinations of 13 things taken 5 at a time. So the probability of getting a 5-card hand of all clubs is the number of 5-card hands consisting of all clubs divided by the total number of 5-card hands. I did this calculation all at once, 0.000495198.079. I'm doing all these calculations on Desmos. Another card hand example, a 5-card hand is chosen randomly from an ordinary 52-card deck. What's the probability that all cards in the hand are the same suit? Well, as we know, the answer is going to be a fraction, and the denominator is going to be the total number of 5-card hands, 52 NCR5. In the numerator, we need to count the number of hands in which all cards in the hand are the same suit. So to get a 5-card hand where all cards in the hand are in the same suit, we make 2 choices. First, we choose the suit, which can be done in 4 ways: clubs, diamonds, hearts, or spades. And then we choose the 5 cards from that suit. And we know the number of ways of choosing 5 cards from 13 cards. It's the number of combinations of 13 things taken 5 at a time. So the number of ways of getting a 5-card hand in which all cards are in the same suit will be 4 times 13 NCR5. And therefore the probability of getting one of these hands with all 5 cards in the same suit is the number of hands with all 5 cards in the same suit divided by the total possible number of 5-card hands. 0.0019807923. So this is approximately 2 1,000ths. So out of every 1,000 hand, you would get a hand consisting of all 5 cards in the same suit approximately 2 times. Another 5-card hand problem. 5-card hand is chosen randomly from an ordinary 52-card deck. What is the probability that the hand contains 3 jacks and 2 sevens? So to get a hand consisting of 3 jacks and 2 sevens, we make 2 choices. We first choose 3 of the 4 jacks. We know how to calculate the number of ways of choosing 3 objects out of 4. That's 4 NCR3, number of combinations of 4 things taken 3 at a time. And then we choose 2 of the 4 sevens. This will be the number of combinations of 4 things taken 2 at a time. So we're making 2 choices. We know the number of ways of doing each of the 2 choices. To get the number of ways of choosing the 3 jacks and the 2 sevens, we multiply. So 4 NCR3 times 4 NCR2 is the number of hands with 3 jacks and 2 sevens. So the probability of getting one of these hands is the number of hands of that type, which we just calculated, divided by the total number of 5-card hands. And when you do the division, you get a fairly small number, 0.000036937852.